Welcome back, everyone. If you've ever watched a fully loaded semi-truck absolutely struggling to get up to speed on a highway while a tiny little sports car just zooms past it in seconds, well, you've witnessed physics in action. Today, we're demystifying the incredible rules behind these everyday observations. In this explainer, we're going to unlock Newton's law of acceleration, completely breaking down the relationships between force, mass, and how things actually move. So get ready to observe, predict, and calculate exactly how the universe dictates motion.
Okay, let's dive into this. I want you to put on your scientist hat for a second. Just look at the world around you. Have you ever wondered why some objects speed up seamlessly while others utterly refuse to budge even a single inch? Like, what is the invisible trigger that transitions an object from resting perfectly peacefully to suddenly moving with increasing speed? Well, to figure this out, we need to strip away all the messy complexities of the real world and look at the absolute basics in a highly controlled environment.
Section 1. What causes acceleration? Discovering the role of forces in motion.
Let's head into our virtual laboratory and take a look at a classic physics setup. This is the Atwood machine. It's elegantly simple, really. Just a light pulley up top, a string, and two masses hanging on either side. Now, right now, both of those gray cylinders have the exact same mass. And because their masses are identical, the gravitational pull downwards on each side is also totally identical. They're basically playing a perfect game of tug-of-war where nobody ever wins. Because these forces cancel each other out completely, the net force on the entire system is zero. And zero net force equals absolutely no movement. If you were to let go of these blocks, they would just hang there perfectly still.
Now, what's really interesting about this slide is what happens when we disturb that perfect balance. We've gone ahead and replaced the right mass with a much larger one. Let's say it's twice as heavy as the one on the left. Suddenly, the downward gravitational force on the right side is way stronger than on the left. We no longer have a net force of zero. We've created an unbalanced force. And if you release the system now, bam! The heavier mass accelerates downward, and because they're directly connected by that string, the smaller mass is yanked upward with the exact same acceleration. We've officially created movement.
So, let's lock in the vocabulary for what we just observed there. When those blocks started moving from a total standstill, their velocity changed. And that is the strict definition of acceleration. It's any change in an object's velocity over time. But here's a crucial detail. Remember that velocity isn't just speed. It includes direction too. So whether an object is speeding up, slowing down, or honestly just turning a corner, it is accelerating. But as our Atwood machine just proved, that acceleration doesn't just happen by magic, right? It actually requires an unbalanced force. This is basically a net force greater than zero that produces a change in an object's state of motion. Think about it like this. If the forces are perfectly balanced, like two people pushing a heavy door from opposite sides with the exact same strength, nothing is going to happen. It's only when one side pushes harder, creating that net force greater than zero, that you actually get acceleration. Section 2. Force, mass, and motion, testing the variables.
So we know we need an unbalanced force to create acceleration. But imagine for a second you have a very specific set amount of energy. What do you think happens if you use that exact same effort to push a really small object versus a massive one? Let's look at a simulation to find out.
In this scenario, we've got a standard wooden crate sitting on a flat surface, and our simulation figure is pushing it. Let's say he's applying a totally constant, steady force. As long as his push is stronger than the friction of the floor, we've got our unbalanced force, and the single crate begins to accelerate forward. It's a pretty light mass, all things considered, so it speeds up pretty easily.
But watch what happens when we completely change the scenario. The same person is applying the exact same amount of pushing force, but this time he's pushing two massive crates stacked on top of each other, plus a person sitting right on top. The mass has increased tremendously. And because the mass is so much larger, that exact same push results in a significantly smaller acceleration. It is going to take a lot longer for this heavy stack to reach the same speed as that single little crate.
So the crucial point is this relationship. When you're applying a constant force, less mass equals higher acceleration, whereas more mass equals lower acceleration. You can think of mass as essentially an object's resistance to a change in motion. The more mass you have, the more stubbornly it just wants to stay exactly how it already is.
Let's keep this momentum going and flip the experiment to test our other variable. What if we keep the object the exact same size, but we change the strength of our unbalanced force? Intuitively, you probably already know the answer, but let's visually prove it.
Okay, we're back to our single wooden crate. This time, our figure applies a very specific measured force of 150 newtons. The crate begins to accelerate. It's a solid, very noticeable change in velocity.
Let's move to 250 newtons and see how this builds when we increase the power. The mass of the crate hasn't changed even a tiny bit, but because the net force is greater, the crate's acceleration is visibly higher. It's speeding up way faster than it was just a moment ago.
Pushing even harder now. We're up to 350 newtons of applied force. The arrow representing our force is getting quite a bit larger. And corresponding directly with that, the acceleration of the crate is climbing higher and higher.
And finally, a massive push of 450 newtons. The crate is accelerating at a really high rate now. Through this whole progression, we've visually proven that if mass is held completely constant, an increase in the applied net force directly equals an increase in acceleration. It's that simple.
Section 3. The Math of Acceleration, from Observation to Universal Rules.
All right, let's slow down for a second. It's time to bring our physical observations into hard numbers. Take a really close look at this data table from our simulation. Notice that we applied a constant force of 100 newtons the whole time. That's the far right column, representing force, which is simply mass times acceleration. Now look at how the mass and acceleration interact to maintain that constant 100 Newton force. When the mass is a light 50 kilograms, the acceleration is a brisk 2 meters per second squared. But as we increase the mass down the column to 100, then 150, all the way down to a hefty 300 kilograms, just look at that middle column. The acceleration drops systematically. By the time we hit a 300 kilogram mass, the acceleration has plummeted to a mere 0.33 meters per second squared.
And this brilliantly illustrates the core mathematical principles of Newton's laws. First up, acceleration is directly proportional to net force. You push harder, it goes faster. Second, acceleration is inversely proportional to mass. Make it heavier, and it accelerates slower. Interestingly, if you were to graph the relationship between mass and acceleration while keeping force perfectly constant, just like we saw in the data table, it forms a hyperbola curve. It perfectly captures how increasing one variable literally shrinks the other.
So why does all of this actually matter outside of a physics laboratory? Well, I'm going to leave you with this question to ponder. How does this exact relationship between mass, force, and acceleration apply to something like road safety? Think about it for a second. When a massive transport truck tries to stop, its immense weight means its braking systems have to apply a tremendous, unbalanced force just to achieve a safe, negative acceleration. A lightweight car, on the other hand, requires far less force to stop in that exact same distance. The math we've explored today dictates speed limits, vehicle design, and honestly how you drive every single day. The rules of physics aren't just dry equations on a page, they're the invisible scaffolding of our entire world. Thanks so much for joining me on this explainer. And remember, keep looking for the forces moving the world around you.